our final speaker for this session. Our final speaker is Deryck Mills, who's the facility manager at the Max Planck Institute. And as some of you guys will know, I'm another structural biologist that's jumped on the EM bandwagon in recent times. And when I was trying to get to know the field and get to know you guys, I went to one of the Gordon conferences, and a tame EMer that I'd found who was showing me around pointed to a guy, I think, sat on a wall drinking a beer, and he said, "Oh, you should probably know this. That guy over there is one of the best microscopists in the world." So I thought, well, I have to go and have a beer with him at some point. It turns out Deryck's a very nice guy, as well as being a great microscopist. So I'm very pleased that he could come over from Germany today to give his talk about the true story behind all these beautiful models we've been looking at.
Oh, thank you very much. Just a moment, I'll just open up. Okay. Do I need to switch it? Oh. Okay. Right, let's get going. For rather a provocative title, True Story Behind the Pretty Models. I'm not going to discuss a lot about the biology here. A lot of you here are new into the microscopy field. Me, I have the privilege to stand up in front of you and have the arrogance to comment most about cryo-EM. I've been in the field a long time now, and I left Oxford 26 years ago to go to Germany. The weather hasn't changed since. To pursue the field of cryo-EM. All right. So, why this title? Well, there's been So if you all look at this, just bear a few seconds, what this playthrough. It'll come up, it'll go up. By the way, this is a paper you should all read. Go through, you start to see metal ions coming in, fine detail here. Come on through. This is the map, by the way, all right? So don't confuse the issues. I've been a little lax with the terms maps and models, but you'll see the reason why. This is the map. Now, those are the more experienced cryo-EM people amongst you will probably notice some noise in this. It's not exactly perfect, but at the time, it was, in my opinion, pretty good. We got it published in a reasonably good journal, and it was actually refereed by Richard Henderson and Nico Grigoriev. So I'm pretty proud of it to a certain extent. Now, this was done back in 2013. This was recorded on a Polara, no direct detector, using film. It took us 2 years to do this structure. It's a 1.2 megadalton soluble protein. It's got a certain amount of symmetry to it. But we were able to get the resolution below 4 angstrom using film on a Polara microscope. A lot of hard work. It took us about 2 years. All right? So cryo-EM, even before these new magical detectors, was possible. Now, the overview of my talk will span 1977 to 2016. That's how long I've been in the field, okay? Cryo-EM are biological structures, the so-called cryo-EM revolution, and my retirement is showing up on the horizon now, and I have a future and some dreams, and these are actually starting to come true. All right, a little bit about me for those of you who don't know me, and this gives me my sort of expertise in the field. I started working with EMs in the 1970s. Cryo wasn't even thought about then. Well, it was starting to be thought about, but it wasn't possible. Then cryo-EM was developed in labs like EMBO in Heidelberg and the MRC. Forgive me if I've forgotten other labs. There were ones that were doing this work at the same time, but I have the privilege to work in both those labs. I gained a lot of experience from people like Henderson, Jacques Debouchier. All those guys were real pioneers in the field. And the first cryo I remember were these structures here, T-phage, viruses in ice. And I was actually taught by Jacques to do freezing and stuff, all right? And in German, they have this nice phrase, Fingerspitzengefühl. It means it's one of those techniques that you either have or you don't have. There are machines to do it now, but it really is an art. And a part of microscopy, cryo-EM, is really developing that skill in art. So all these guys that you have running these facilities, doing the cryo and stuff, people like Daniel and Alistair up there, look after them. They gain this skill, and they're able to image this stuff, but it really is an art. Okay, when I first started doing cryo-EM, this will all come into perspective. We didn't have high-end microscopes, and I've heard that term say a lot here, high-end microscopes. And people automatically think of a cryos. Well, I'll try and change your view a little bit on that. When I first started doing cryo, I did it with machines like this. They were not designed for cryo. No cold stages, no low-dose systems. You basically had to trick the electronics and the optical alignments and stuff to obtain images. The vacuums were so bad, you maybe have a 30-minute time slot to collect your data and stuff, but it was doable, and that taught me a lot about how to proceed and go with this. And the actual media at the time, up until about 6 years ago, was still film. There were CCDs around, but film was by far the best media. As an EM facility manager, or someone that's responsible for cryo-EM, I have to consider a wide variety of biological samples that want to be imaged, all right? You know, the asymmetric stuff like the ribosomes, virus particles, helical arrays, 2D crystals, unique structures here. Basically, I've said that because of tomography. Cryotomography is a growing field, but it's actually originated from these, all right? Believe it or not, I have a boss in Frankfurt, Werner Kubrand, and Werner established himself in the field of cryo-EM, and this was the initial starting point for cryo-EM. In the days, we couldn't do single particle stuff very well, but we could do 2D crystallography, particularly of small membrane proteins. And Werner established himself while he was at EMBO in Heidelberg and produced one of the first high-resolution structures of a membrane protein, LHC. And this was obtained from both images and electron crystallography. Right, the thing that we've all been talking about and why most of you are here is because of this. This was a paper, again, written a couple of years ago by my boss, Werner, and he highlighted the revolution that took place. There's three sorts of proteins here, basically. You've got the mitochondrial ribosome, this small trip channel, this iron thing, and my own baby here at the end. They're all showing high resolution, fine detail and stuff like that. And this really started to make people sit up and think that cryo-EM really can do things for us. And we're starting to knock on the X-ray crystallographers' doors. And then last year, I know this has been discussed before, and some people say, well, maybe this is not at 2.2 angstrom or things like that, but I think this is a remarkable piece of work. All right, the protein's out of a bottle, but what the heck? I mean, you're below 3 angstrom now. And if someone had asked me about a year ago, maybe a little longer, if 3 angstrom was ever possible to go belong with EM, I would have said, maybe not in my time. But I was proven wrong. And why? Okay, now what's happened is that things have all come together. EM or cryo-EM at high resolution hasn't just come about because of these cameras. It's evolved. And it's evolved around all these 6 points. And facilities like you're setting up here cover all these points. And that's why they need to be pursued and pushed forward. The EM lab itself is a critical component of this. You shove a microscope in the wrong room, you ain't going to get much out of it. There's the microscopes, the cryo-preparation, the electron detection, the image processing, and data management. That all has to be taken into consideration. You screw up on one of these, you ain't going to get anywhere. I do cartoons, and EM is not cheap, all right? Let's put it in perspective. You need a big budget. The microscopes alone, I'm a bit out of touch with UK prices, but a microscope alone is about, we say a cryo, something like 4 or 5 million, all right? In order to really push things away and things, you have to, before you venture into this, have a good budget, know how to organize your budget, and have a budget that will sustain you through a period of time. I'll give you an example of the units we have in Frankfurt. Max Planck is a wonderful institute to work for. There are probably Germans in the audience. It's a privilege to work for them. They're basically a tremendous organization that really supports high-end science. It's well financially supported, and it has a really nice infrastructure. But my unit itself has 3, what you call dedicated, I call them dedicated cryo machines. I got 3 smaller EMs for screening, FIB-SEM. And this is the breakdown of the people using our unit. We do a lot of collaborative studies, but we have 50 people in the group basically, but about 50% are doing EM. And that splits it down. About 6 years ago, this ratio would have changed a little bit, but single particle was really taken off. So, because I've been in this field so long, I get a lot of requests for setting up EM labs and using a consultancy away and stuff like that. I try to help people as much as possible, but I always give them this slide. Basically, these are the things you have to really consider before you jump into this field. And I'm not exaggerating about any of them. And the last one, which should pop up in a second, who can I ask? Well, any of you that are going into this field should firstly go to a well-established EM lab that's producing results, look at how they've structured it, how they financed it, and gain your experience there. Our lab in Frankfurt has an open door policy, so if anybody are interested, come, by all means, give me an email, and you can come by. I'm very proud of what I set up in Frankfurt. This is the basic structure of it, but I've always felt that cryo-EM should be an easy technique. It should be such that the biologists can come in, do their applications, not worry about fine optical alignments, contamination, whether the right bits and pieces are in the lab. So I've structured the lab such that it's a satellite system, whereby you have a central preparation area and all the microscopes and ancillary equipment around it. So everything you need is in that environment. It's rather large. Germans are very generous with space. This is something like 500 square meters, all right? And it's mechanically very stable. It has a nice climatic system. I got reduced humidity, precise temperature control, everything that makes cryo-EM easy. The microscope itself, we all think of high-end cryo-electron microscopes. All microscopes can be adapted for cryo. It depends on your skill, expertise. But you certainly couldn't buy something like this. So, high-end microscopes, all right. I smile to myself when I hear this baby here being mentioned. It's a very nice microscope. But it's the latest of a series of high-end cryomicroscopes that are developed. It's not only changed its sort of outward look, there's a reason for that. It's gone away from the conventional cryo-EMs that people use. Basically, they've encased it in here such that they can make this microscope modular. By modular, FEI want to make money from these machines so they can adapt any machine inside this box to the customer they're selling it to. The Cryos basically has all these modular lenses on it, and you can add to it. You can put correctors in it, phase plates and stuff like that. By encasing it in a box, you can open it up, jack it up, and do it. Other microscopes I have in my facility, I have this one here. Not many of you know this. It's Joel 3200. And my oldest one is a Polara. All these are fitted with direct electron detectors. They've all got, in my opinion, what's essential for cryo-EM, particularly biological samples, the energy filters. And they all have very stable cold stages. All right? And that's where microscopes, even back about 5 years ago, cryostages, or the mechanics for cryostages, become really good. You can put things in there for long periods of time without things drifting in that. And with direct detectors, where you're collecting movies now, and routinely for smaller membrane proteins, where you need to collect longer movies to get more dose and signal, then stable stages are good. You've all read about the fact that you can correct for movement and stuff, or you can correct for a certain amount of movement. You can't if it's running across the screen. Whenever I have an electron microscope or want a new one, particularly one of these cryo ones, I have 17 points that they must fulfill. These usually put the fear of God into companies like FEI or Joel, but they're all obtainable and they're not unreasonable. And there's something your microscope should all have if you're going into this field. It should fulfill these specifications. Another feature that's essential for EM is this stuff, cryo-EM. It's looked over a lot. It's the medium from which you're going to do all your preparation, all your freezing. If this stuff is contaminated, it ruins your preparations. You need to keep things really clean and quiet, very clean. So I have my own supply there. I've got 3,000 liter. It's basically iron tap. The next thing you need to consider, now this has been a revolution as well, is the support films for cryo-EM. There are a magnitude out here now. When I first started cryo-EM, we used to make our own lacy carbon films. Maybe some of you remember them. But what these films have enabled you to do, enabled you to automate data collection. Also, the films have become more stable, and the hole size and shape, the substrate that they're on, can all help with good cryo data. I'm starting to use these gold films now. You have to change your process at where you want to image them. You can't obtain tone rings or anything like that. You need to adjust your focuses on the edge and stuff like that, or use other ways of looking at the diffraction pattern maybe to precisely align things. But what they do, which is really neat, is that they stabilize the Z movement. Most people just think of the XYZ movement. The gold grids actually stabilize it in this direction, and you do get that with cryospecimens. Graphene I haven't used much at the moment. The other thing which is very, very nice as well, and you've probably all encountered this, particularly those people that work with membrane proteins. They're renowned for difficulty of going into the ice. Well, if you change the shape of a hole, you can actually change how things go into the ice holes. And we found that using these elliptical ones, quite often, proteins that we could never get into ice, we find cluster around the elliptical apexes of these holes. It's really very good. And I think it's something to do with the way the ice forms in that medium. All right, freezing. This is the real tough part of any prep, I think. I've put up some, not the ultra-modern things, like you can have new Vitrobots, you can have things from Zeiss, Gatan, all sorts of freezing stuff. I've even made my own. But these are the real critical thing that you need to master for good cryogrids. It's not only the good distribution of protein, it's a good quality ice. Why? You make the ice wrong, you get the wrong distribution. You can even get preferential orientations. Now, you've all been mentioning microscope time. I can't get on microscopes and stuff like that. Well, believe it or not, we have the same sort of problem in our institute. People want to use microscopes. There's more and more coming in. So I've had to think up of other ways of alleviating this problem. What I've done is I've modified specimen holders, or my workshop has, so that I can make things in cryoscrid holders and either put them in the Joule or put them in the Polara. Also, I cater for long-term storage or multiple viewing of specimens. Quite often you get a good grid, beautiful ice distribution. You maybe got 1 day on the scope. You want to put it back in. So what I've got a workshop to do is make special holders that can actually securely keep the cryo-preps from the various microscopes stored so we can re-put them in. And if you retain them in these holders, you put them back in. You can go back to the coordinates that you previously viewed and carry on your data collection. The other thing is that making the preps is sometimes very difficult. So people will freeze whole batches of samples. So what I've done is had multiple long-term storage containers made so that we can store things cleanly and under very stable conditions for long periods of time before visualizing them. All right, not everybody can afford a Cryos or a top-end machine. These still exist, these side entry holders. And they're quite useful for pre-screening or optimizing your cryo-preps before putting them in a big machine. Obviously, some of you come here to collect data and stuff. You have a smaller machine back home. Check the samples out. Check 1 or 2 of your frozen preps before you rush along and get your data set. It's all about timing and preparing yourself. These are the sort of criteria I use for these sort of things, but there's still a lot of F20s around, F30s around that use these, even some Joule microscopes. You can still buy modern microscopes from FEI, things like the Thales that still utilize these cold stage holders. They're more difficult to use, they require more skill, but it's doable. The cryopreparation itself, I mentioned this earlier. You want all these things to be fulfilled. But ice has strange properties. And I use this as an example. You make the ice too thin here, and you can actually change the shape of the protein you're looking at. Orientation of proteins. All right. 2 rather nice preps I made. One on the left here, looks beautiful. The one on the right, that looks okay. The one on the right went to 3.2 angstrom. This baby here stuck, basically because all the protein is basically in preferential orientation. I thought I was doing something clever. I always thought I increasing the protein concentration, visualizing in ice, just marginally thicker than the protein itself. Big mistake. It can often lead to this sort of thing. And you have to be careful. And this is where I mentioned something about energy filters. Well, we all have energy filters. I won't go into the physics of how they are, but basically what they enable you to do is visualize things in thicker ice. And believe it or not, membrane proteins love thicker ice. So if you use just use it in zero loss, you can image things really quite nicely with an energy filter. I'll give you some examples. All right. We are another group that works on ATP synthase, something we published last year. It's rather nice. But you'll notice, the more observant of you here, TMV. I incorporate this in a lot of cryopreps. It helps incorporate or stabilize the protein in the ice, the one you're looking at. In my opinion, what the TMV does, it acts like a boon, those sort of things that you put in to stop oil spreading over water surfaces. Most of the membrane proteins you look at, detergents, lipids, and stuff like that, and that affects the way they go into the water, the way they distribute, or they stick onto the carbon. By incorporating something like TMV in there, I can actually stabilize the protein of interest in the ice. The other thing that you have to be able to do is that when you're looking at something like this, and these are ATPase dimers, is recognize the particles in the ice, all right? So you can imagine, this is probably obvious to some of you, a protein will go in a sort of like a preferential orientation. But can you recognize it when it's like so, or like so? And Richard Henderson always told me, if you can't see it, you can't pick it, you can't process it. So you've got to be able to see it, all right? So know your protein. This just goes through some class averages. And next thing I've started to move on to, and this is where my talk gets a little bit more lighthearted, is you process your data, you get your class averages, and what you all want to do is produce something like this. You want a lovely map in which you want to dock in your model or build your model. And model building, as Sean pointed out earlier, is not trivial. You need expertise for that. You need a skill for it. And quite often now, we can produce nice maps. And we have one or two people in our group, we're very fortunate, that can actually do this model building. And they are essential for pushing these structures to this sort of detail. But without a good map, you won't get a good model. All right, I'll quickly go through this because maybe running a bit short. Low dose. Low dose, you're all familiar with it. It's a standard routine. All scopes have it. What does it mean? Basically, nowadays, what it means with new detectors is you have to be able to visualize the quality of your ice before you image it. You need a good search media. All right, and in the past, one could do this quite easy like this. You'd set it up, so you focus adjacent to the area. You've all done this, recorded photographs, gone through, record an image. Well, with the new detectors now, the new detectors, as Dan mentioned earlier, you can do rather tricky things. You can do things that enable you to do automated data collection. What you can also do with these things is make sure that each image you collect is next to perfect. So quite often what I do is multiple sampling. If I'm using something like a cryos microscope, you have this nice little feature called nanoprobe. Well, nanoprobe enables you to, at a certain pixel size, contain the beam to a very small probe size so you can do multiple sampling of holes. So you actually can pick out the areas in the ice hole that have the best distribution of protein. What you can do also is focus and adjust your optics perfectly before sampling the area. Now, what the direct detectors have allowed us to do now is adjust our optics of our microscope and to tune everything at the dose that we want to collect our data at. And that's an important factor to remember. In the past, most microscopists would use a much higher magnification, higher dose to adjust things like astigmatism and stuff like that. Well, now you can, with these direct detectors, you can actually tune your optics at the incredibly low dose that you need to collect your data at. And that's what makes Cryo-EM now so successful, being able to utilize these cameras and collect data which is optically next to perfect at the magnification or pixel size and the dose that you want to collect it at. Okay. Oh, sorry, I'll go back one. What these grids have allowed, and we use these automated programs just like the rest of you, Cryo-EM, Leginon, EPU. I'm not going to say which is better, which is worse. They all work remarkably well. But they only work as well as if you've set the scope up well to start with. Don't assume that these programs can run really perfectly without some initial alignment or optimization. They won't. All right, the past media, detectors, films, still used. Basically, we used film up until about 3 years ago. It's obvious reasons why it's no good anymore. But now, what we have are these things. I'm very fortunate at MPI. I have a lot of these things. Sounds a little bit arrogant, but I have a K2 on each one of my microscopes, and on one of them, I have the new Falcon 3, which has so-called counting mode. The two cameras are slightly different. I think there's another one from DE, the direct detectors, which the gentleman from Berkeley. I have no experience of that one whatsoever, so I'm not going to comment about it. These two cameras, in my opinion, are exceptionally good. They operate in slightly different ways. One of them is a true counting camera. The other one is an integrated camera. They have different readout speeds. This top one here reads at 400 hertz. This one here, 40. The new Falcon 3 reads out about 40 frames a second. This one, I suppose, 400 they say, but it depends what you want to set it to. All right, the reason they're so good is basically they've overcome this problem of your signal needing to be converted through these fiber optics and scintillators. And then, by really thinning this chip down here, you can get incredible sensitivity with these things. And the latest cameras for Gantan and FEI have even thinner chips. And the development of these is even proceeding at the moment. All right. Data processing. All right. Data processing has come into its own force. People like the Gentler Shores yesterday have really revolutionized how we can deal with our data. Aligning the movies, sorting the best images out and stuff like that. They've all complemented the way we utilize microscopes. This movie here shows you how good these new cameras are. And basically what I've done, I've got an ice crystal on top of vitreous ice. Now if you look, one on the left is not aligned, the one on the right is aligned. Now if you can do that with ice, you can do it with protein. And this is a real test for a camera. It's one of the first experiments I did with these things, and wow. Right, this is all you've all encountered, raw aligned movie, aligned movie. The movies that you attain now, and this is something I've learned with these new direct detectors since I've had them, the longer the movie, the better it is for smaller particles. Quite often, routinely now, I collect 8 9-second movies, which generate between 40, 50 frames. In the past, we knew that the movie length would give us a total dose of something like 50, 60 electrons per square angstrom. And we used to worry that maybe that amount of dose you'd be zapping off all the various protein details by the time it got to the last frames. Well, there's some neat programs out there now, things called Unblur is a good example of one of them, particle polishing and things like that. Basically what they do is if you're precise enough with your dose, you can actually back extrapolate in the processing to get the best from the detail of the particle as it goes through this degeneration. Very early movie images that I did, we would actually chop out the first frames. We would do our initial alignment with the big long movies and then keep chopping them back and back until we got the best resolution with the frames that give us enough signal to noise. And at the end of the day, it's all about signal to noise. Picking particles? Well, sorting the best images. Well, you all know this. Obviously, you want to record the best data. We still use tone rings for sorting things out. And this just shows the effect of a line in a movie after something has been in. This is a little bit exaggerated. I did it straight away just to show how well the camera was working. So you get the maximum effect for it. Normally, when I'm recording super resolution data, the speed at which it takes to save the image and before it records the next. In some of the best microscopes, this sample is so stable, you need to do very little alignment. What alignments you need to do basically come from the actual movement of the protein itself, not from the mechanical drift. Picking particles, well, this can be done quite easy now. You've got a beautiful sample like that, pick them, you've got to recognize them. I won't dwell on that point. Again, making your class averages, classifying the particles, that's all common knowledge to a lot of you. Right. Image processing and particle reconstruction. This is, again, quite critical. And you remember the image I showed at the very beginning of things. It's the same molecule. We did this one with Matteo Allegretti, and we reconstructed it to 3.2 angstroms in just a few weeks. Actually, it was just 2 data collections. My initial work on film was weeks of data collection, all right, sorting out the negatives, digitizing them. So this is the real speed of this technique now. And this is another one we just under review. This is a much smaller protein, 600 kilodaltons. It's a beautiful map. We got this one to about 3.5, no, 3.3 angstrom. Looks nice, and it's going to morph into the map in a second. It's under review, but this one was done in just a few weeks. I now use this particular protein for testing my microscopes. I basically, if I have worry about something not reconstructing correctly or something's wrong with the processing, I have many of these grids made up. I can shove it in there. I need to collect maybe 30,000 particles, which comes from about 50, 60 images. Quickly process that, sub 4 angstrom, okay, I'm happy with things. It's lovely to have a cryo specimen that you can put into your scope and test the machine to how you want to use it. It cuts out a lot of heartache. Realistic biological relevance. Quite often when we're looking at new samples and stuff, I use the features that you can resolve in the maps as a guideline to how you can proceed, all right? So with about 8 angstrom, you start to see alpha helices. 5 angstrom, the alpha helices start to get their nice little spring turns in them and stuff like that. And they're what I call signs of encouragement, all right? When you get a new sample, you're playing around with it. And these things you can really use now to help you. And actually at 4.7 angstroms, you can start to see a separation of beta strands. At 3.8 angstroms, you see most side chains. And at 3.5 angstroms or below, you start to see most side chains and metal ions. And this is something I was given the other day by one of my group. It's another protein we're reading on. It's under review. I'm not going to discuss the resolution. I'm not going to discuss the details of it. But this is something that is going to really push structure a little bit more. And this is another map of ATPase dimer where we really are starting to put things together. So what I've got working in our lab can really work. And 3D-EM maps. I put together a little collage. This is not all the structures we do in our lab, but it's most of the ones I've been mostly involved with. The top line here are all soluble proteins, varying sizes from 300 kilodalton up to 2.6 megadalton, I think. And then the bottom 2 lines are various membrane proteins. Smallest baby here is around about, the smallest thing I've been able to image is around about 120 kilodalton, all right? Okay, the future and problems to solve. Microscopy is doing really good now. We've put the fear of God into X-ray crystallographers, and these are the problems I still think that we need to work on. Sample preparation, heterogeneity. As Sean pointed out the other day, one of the things that really kills us is when proteins are starting moving around. Oh, that is real, really annoys you. And there's another thing that's really been highlighted to me recently, is how protein can be disrupted at the air-water interface. You see the proteins breaking down and stuff. Sometimes you think it's a fantastic prep, it looked great in negative stain, you put it into ice, you see the particles, fragments. And I think this is a problem here. Sample flexibility. EMs, we all think they're great, they're cryos. Well, I've been very fortunate. 3 weeks ago, we got funding for another cryos. All right, something, oh, great. But what I've asked for, and we actually get this machine in November, I've asked for even better specs on these machines. And we all know we buy these machines and we want them to, Max Planck's, every 10 years we can look at maybe finding the funding to renew them. In theory, most microscopes have to last you about 15 years. What I've asked for now is an improvement. And these are the things that I think are the problem at the moment. The vacuum or contamination rate on these big microscopes is far from perfect. People say they collect data for 24, 40 hours. you should measure the contamination rate of any one high-end microscopes and see what the contamination buildup is. You'll find by the end of your data collection, a lot of the fine detail is being suppressed by ice condensation on there. Improvement in optics. Optics are still not perfect. The alignments, the guns. The latest generation of electron guns, the so-called XFEGs, are fantastic. They give better coherence. The new lens designs where you have the triple condenser system, where you can have parallel illumination. They all help in your optical alignments improvements. Correctors and phase plates. I'm a big fan of correctors. One, because I worked on their development when I was in Heidelberg, in electron optics, CS correctors. And the reason I'm a fan of these is that by having a CS corrector parked below your specimen, you can actually tune the optics of your microscope to near perfection. No beam tilt, no coma. So you can really record optimum data. And when you want to push things to that high resolution, it means your optics have to be really good. A good example is you put a little bit of beam tilt into your data collection, and then you try collecting data beyond 6 angstrom. An interesting experiment. All right, the last thing is, and this is already being worked on, I'm part of a consortium that's developing the next generation of direct electron detectors. They're going to become faster readouts, quicker, bigger. That's already underway. You'll probably see the first versions of those next year. The other thing is movies, data coming off. We want to be able to process it quicker. But what we need to do is make sure the data coming off is quickly analyzed so we can tell if our protein is right conformation, right distribution, before we collect 100,000 images or something like that and find it was wrong. What we need to do is better pipeline this data, check the quality, not only of the optical alignment and stuff, but of the protein distribution. That is already being pipelined, and there's groups, I even know that people here are working on that. That's something that's taking place. Then, the last thing, which is my headache at the moment, is data management. I don't know about the rest of you guys, but we collect magnitude amount of data. We're having to rethink how we store stuff, how we save it, what we need to save. It's something we're trying to deal with, but at the moment we just keep buying more and more space. Then, ultimately, my dream, and this will come true, and I'm hoping to fulfill it by this date. I would like the ability to prepare cryosamples that are directly sprayed to a grid rather than blotted. I would like the ability to be able to really analyze cryopreps in a screening machine under the conditions that I need to load them then into a high-end data collecting machine. Keep the two together, apart as it is. Then, this is my real dream, is this sort of electron detector. And this is coming true. And this will really revolutionize how we can really collect data. And finally, my last little cartoon. And won't dwell too long on it, but it's all about publications, structures, things like that. Let's not kid ourselves. We all need to get high-resolution structures, publish them, let the world know what we're doing and how we're spending public money. Lastly, no EM unit cannot work without a team. I'm internally grateful to the Max Planck Gesellschaft or Max Planck Institute for giving me the opportunity to be able to put together this EM facility in Frankfurt, Germany. I'm endowed to my boss, Werner Kubrand, who's always supported me, given me a lot of trust, and he's been absolutely fantastic. Janet, who's an incredible single particle person, but she can do fantastic modeling, constructions and stuff. Without her, a lot of the models we couldn't have done. And then Matteo, Eduardo, Alexandra, and Karan all work fantastically with the ATPase synthase work. Bertram, who's one of our tomographers in that, working fantastically with subtomogram averaging. Arnie Muller, who just joined us, has been very implemented in putting together automated data collection. Arnie is an expert in Leginon, which has been really a fantastic help. Then my two IT guys, Juan, well, Oscar's not one of my, actually, he's an independent scientist, but he's a guru with IT. My EM staff, Frederica, Simone, and Suzanne. My workshop. And two people here, Richard and Greg, who taught me a lot about direct electron detectors, the very first ones. Greg even instructed me how to hack into fiber optic networks, which is quite useful when you want to read out some of the early data from some of these cameras. And with that, I'd like to thank you all for your attention, and I'll take questions from the audience, if there are any.
Thank you very much, Deryck. Questions?
Probably not. Yes.
Hi, just a simple question. Can you use nanoprobe mode on the Cryos with tomography as well as single particle?
Sorry?
The nanoprobe mode where you have the small beam restricted to a small working area, can you use that for tilt series as well as for single particle?
You can use it for any data collection mode you want, yes.
Okay, thanks.
Yeah. It's a feature every Cryos or FEI machine should be used in, all right? You should never use the standard. You should always use nanoprobe. It's by far the most optically stable and best way for sampling things. Yes?
You mentioned sample storage, and perhaps you could comment on the future of remote data collection, shipping samples around, finding the best microscope for the experiment.
Sorry, could you repeat your question?
Shipping samples. Can you do remote data collection if you're shipping frozen samples?
My way ultimately would be to have masses of these. You're probably all familiar with these cassettes that you have for the Cryos or the autoloaders. My idea would be have something like these cassettes that we could use for long-term storage of specimens, categorize those, but they're incredibly expensive. One has to make, so you minimize the amount of physical interaction you have with manipulating your grids. Cryo specimens are incredibly sensitive to disruption, contamination. So once you froze them, if you can get them into the capsule that's going to be loaded into the microscope, you can minimize that contamination and any destruction of your sample itself. That's the way I would go for it, but there's a cost factor in this. Storage, well, we're like any other laboratory. We've got, probably most of you got stacks of these dewars sitting around your lab with lots of specimens in that. That has to be really well organized. Fortunately, I have some technicians that take care of that for me rather well. Yes.
Yeah, I was just wondering whether you can suggest a routine or a way to check for when the buildup of contamination becomes such that you want to change the
Very
grids.
good question.
Since you mentioned you cannot collect for more than 24 hours. Or...
What I do is I consider that most microscopes, after about 12 hours, then you've got contamination buildup on your grids, which is probably suppressed in detail. I would try and minimize the time that you use for your data collection, then take it back out, wash it with fresh nitrogen. The other thing you have to bear in mind with most microscopes, particularly the Cryoses or Thales Arcticas or things that park things in a parking bay by the side, the vacuums in those parking bays are far from perfect, generally for two reasons. The pumping systems that they design there, turbo pumps in that way, can cause interference with your data collection. So what I do, once I get a good sample in, I've screened mine, I take all the other ones out and store those in nitrogen. Keep your samples under liquid nitrogen and only have them in the scope for the imaging. That's the best I can come up with at the moment.
Okay, if there are no further questions, let's thank the speakers again.